Now we are going to discuss some variant of principle of mathematical induction. So what does this variant involve? It can be clear from the variant 1. There is some variation to get result. That is, if Pn is a statement involving natural number n and if P of k naught is true for some positive integer k naught and if the truth of pk for some integer k greater than k naught implies the truth of p of k plus 1, then Pn is true for all n belong to n such that n is greater than equal to k naught. So what is the variation in principle of mathematical induction? Variation is that here k naught may be 1, 2, 3, 4, 5 and the principle of mathematical induction will hold for that result for all n natural number greater than equal to that k naught. That is the main variation. It is a variant 1. So on variant 1, based on variant 1, we are going to solve one example to understand the variant 1. So example say that prove 2 raised to power n greater than strictly greater than n square for all n greater than equal to 5 and n belongs to natural number. So here we can see that k naught is 5. So the solution is same. Let p of n is 2 raised to power n greater than n square. Here k naught is equal to 5 which belongs to natural number. Then left hand side, that is p of 5 is equal to 2 raised to power 5, that is 32. And right hand side, that is p of 5 is 5 square, that is 25. So it is clear that 32 is greater than 25. Therefore, P5 is true. That is, Pk naught is true. So this was the first step, not involving 1. Now, as result of k naught implies some positive integer k, that is pk is true. So let pk be true for a k n is k greater than equal to 5, hence 2 raised to power k is greater than k square. After that, we have to prove the result for p of k plus 1. That is in the variant 1, that is if pk naught is true for some positive integer k naught and if the truth of pk for some positive integer k greater than equal to k naught, that is k greater than equal to k5 implies the truth of p of k plus 1. So we have to prove the result for p of k plus 1 by using the result of p of k because it implies the So let n is equal to k plus 1. So we take left hand side, that is 2 raised to power k plus 1. That is 2 raised to power k into 2. As 2 raised to power k is greater than k square, then it becomes 2 into k square. That is 2 raised to power k plus 1 is greater than 2 into k square. Now we have to make the result that we have to prove, that is we have to prove what is that 2 raised to power k plus 1 should be greater than k plus 1 whole square. So we have to convert this result near about, or near about, not near about, it is absolutely greater than k plus 1 whole square. So as k is greater than equal to 5, that is, we can say that k square is greater than 2k plus 1. How can we say that? For all, because we can check out 5 square is greater than 11, 6 square is greater than 13, and so on. So we can say that k square is greater than k plus 1. So we will use this result. So it is a trick. We have to mind it carefully. How can we get this result? That from 1 we have 2 raised to power k plus 1 greater than 2k square, which is also equal to k square plus k square. But we write here k square is greater than 2k plus 1. So 1k square is replaced by 2k plus 1. That gives, it is equal to k plus 1 whole square. That means 2 raised to power k plus 1 is greater than k plus 1 whole square for all k greater than equal to 5. So p of k plus 1 is true. That is, p of k is true implies p of k plus 1 is true. So by the variant 1, p of n is true for all n belongs to n, such that n is greater than equal to 5. So that was the variant. In this there is a little difference, that we have to prove result for some positive integer k naught, which may be 1, 2, 3, 4. There is some restriction. This result is due for some particular level.